600 miles of ocean separate these two cormorants. The mainland bird can fly. The island bird cannot. How has this one species, out of all the members of its order, lost this most characteristic feature of birds? Charles Darwin did not see the flightless cormorant during his historic visit to the Galapagos. It was not discovered until 1898, presumably because it exists only as a small population, confined to a restricted area of the coast of the two westernmost islands of the archipelago, Narborough and Albemarle. However, it did not evolve by itself, but as an integral part of the Galapagos ecosystem. The rocky shores and productive waters it inhabits are shared with an unlikely group of associates. The marine iguana helps us to understand the occurrence and possibly the evolution of the flightless cormorant in the Galapagos. The equatorial currents produce strong local upwellings of nutrient-rich water, which provide an abundance of food. This high productivity maintains a persistent algal bloom that makes the water greenish and murky, a marked contrast to the clear, transparent waters characteristic of the high seas in the tropics. The shallow water and rocky bottom along the coasts of Albemarle and Narborough Islands support the rich underwater pastures on which the marine iguanas graze, and also provide a habitat for the eels, bottom fish, and octopus on which the cormorants feed. Galapagos cormorants need sheltered inlets and bays to protect their landing sites from the heavy wave action generated by the southeast trade winds. The many lava flows in Albemarle and Narborough provide sloping shores that make ideal landing ramps and create stretches of sheltered water, in which the cormorants carry out the aquatic phases of their courtship. The head shaking and intertwining of necks, which are conspicuous elements in their courtship display, begin in the water and continue on land. Unlike birds which can fly, the Galapagos cormorant has lost the keel on its sternum, and its flattened breast allows the pulsations associated with its courtship vocalizations to be clearly visible. Cormorants with functional wings spend a good deal of time sunning and drying them after they've been in the water. Although the wings of the flightless cormorant are small and degenerate, it retains the wing drying behavior of its flying relatives. Flightless cormorants breed only once a year, but the breeding period is protracted and peaks during the relatively cool season, which corresponds with the northern hemisphere spring and summer. Their nests are built of seaweed and are usually located only a few feet above the high tide line. They nest in the same areas year after year. The barren lava flows on which they build their nests expose them to the full effect of the equatorial sun. The adults must continuously shield their nests from the solar radiation to prevent the eggs from becoming addled and the chicks from dying of overheating. The intense heat causes the adults to employ evaporative cooling by fluttering their gular pouches. This evaporative cooling removes water from the body fluids, which in turn activates the nasal glands, the secretions of which flow along the bill and drip from its tip. Normally 3 eggs are laid, but all 3 rarely hatch. Even when 2 chicks hatch out, ordinarily only 1 survives. The newly hatched chick has tiny wings and relatively enormous legs. The small size and undeveloped condition may contribute to the high level of nestling mortality. The young bird begs for food by lowering its gular pouch, which has a characteristic white marking, shaking its head from side to side, vocalizing and tapping gently on the bill of the adult. The parent then regurgitates and the young practically dives into the adult's stomach to obtain the food. Even when the young are almost full grown and have become effective swimmers, they still demand that their parents feed them. Since this cormorant's loss of the capacity to fly occurred at some remote point in time, the causal factors can never be identified with any degree of confidence. It offers, however, an excellent example of the genetic loss of a functional capacity, made possible by the safety and lack of competition associated with isolation on remote oceanic islands. This isolation, together with a locally abundant food supply, suitable nesting sites, and an absence of terrestrial predators, presumably resulted in a situation in which individuals with ineffective flight machinery were not eliminated by natural selection, and so perpetuated their deficiencies. The alternative hypothesis, that the evolution of flightlessness was advantageous and positively selected for, cannot be rejected, but it presents many difficulties. A partial compensation for the reduced wings is supplied by the legs of the flightless cormorant, which are relatively much stronger than those of related forms that can fly. However, losses of function in birds can affect other mechanisms than flight. For example, the tropic bird has lost the capacity to walk and moves on land with a laborious crawling motion. This red-tailed tropic bird was photographed in the leeward chain of the Hawaiian Islands. The wings of some flightless birds have acquired an alternative locomotor function. The same area in the Galapagos that is occupied by the flightless cormorant supports a substantial population of small penguins. Their wings, however, are not degenerate, but are modified into flippers, with which they fly through the water. The case of the flightless cormorant is analogous to that of blind cavefish. These cavefish live in perpetual darkness, and natural selection has not eliminated those individuals which have lost their eyes. The flightlessness of the flightless cormorant is important, not only because it shows us how a major function can be lost through the relaxation of selective pressures for its maintenance, but also because it demonstrates that natural selection is as essential for maintaining the status quo as it is for producing new, adaptive changes.